Welcome to the 13th lecture on electrodynamics for Bsc students. Today's topic is Poisson and Laplace equations. Two equations are discussed here. They are Poisson equation and Laplace equation, electrodynamics, 13th lecture. What is Poisson equation? You know the spelling. Poisson equation. The Poisson equation is del square psi is equal to minus rho by epsilon 0, not the minus psi. Del square phi, not the psi. Del square phi is equal to minus rho by epsilon 0, where phi is the potential function. Or we can write del square v. Capital V is a potential function. Here we take the symbol phi for potential. Del square phi is equal to minus rho by epsilon 0, where phi is a potential function. This is a Poisson equation. In this equation, you know del square is del dot del equal to dou square by dou square plus dou square by dou y square plus dou square by dou z square, repetition operator. You studied the second degree three-dimensional operator, differential operator. Del square. Rho, you know, volume charge density. And epsilon 0 is the permittivity of free space. And this is a Poisson equation. And you note the Poisson equation is a modified form of Gauss law. Gauss theoremത്തിന്റെ Gauss lawയുടെ ഒരു മോഡിഫൈഡ് ഫോമാണ് പോയിസൺ ഇക്വേഷൻ എന്ന് മനസ്സിലാക്കുക. del square phi is equal to minus rho by epsilon 0 എന്ന് പറഞ്ഞാൽ നമ്മൾ നേരത്തെ പഠിച്ച phi is equal to 1 by epsilon 0 q എന്ന് പറയുന്ന ഗോസ് ലോയ്ക്ക് തുല്യമായിട്ടുള്ള ഒരു ലോയാണ്. പക്ഷേ ഇത് സെക്കൻഡ് ഡിഗ്രി ഡിഫറൻഷ്യൽ ഇക്വേഷൻ ആണ്. അപ്പം അങ്ങനെ ആകുമ്പോൾ കുറച്ച് അഡ്വാൻറ്റേജ് അതിനുണ്ടാകും. അതാണ് ഇവിടെ പറയുന്നത്. So you understand the Poisson equation is del square phi is minus rho by epsilon 0. Phi is the potential function. The potential can be represented as a function. And now we see its proof, derivation. And for that we start with the differential form of Gauss law. You know the Maxwell's first equation, field equation. Differential form of Gauss law, del dot T is rho by epsilon 0. There is no minus here. Del dot T is rho by epsilon 0, equation 1. And we have studied the last class. Electric field is equal to minus del V, negative gradient of potential, where V is the potential function. Here we use a symbol phi for V. Instead of V, we use phi. So we can write E is equal to minus del phi, since V is equal to phi. Therefore, equation 1 becomes, in equation 1, we put this value of E, that is E is equal to minus del phi, is put in 1, the Gauss law. That is V into minus del phi. You can put a del phi in a bracket, a minus del phi in a bracket. There is into a minus del phi you can put in a bracket. Is equal to rho by epsilon 0. And minus sign is taken out of the bracket. Del into del is del square. Del square phi is equal to rho by epsilon 0. That is minus sign is taken to the right. Del square phi is equal to minus rho by epsilon 0, equation number 2. This is the Poisson equation. And it is a very important equation, Poisson equation. Like Laplace equation, like Gauss differential form, this Poisson equation is also an important equation. Here charge density is rho. Phi is the potential function. And next is Laplace equation. Laplace's equation, or simply we say Laplace equation. Laplace equation is modified form of Poisson equation. You look here. Laplace equation is a special form of Poisson equation, Poisson's equation, in which electrical charges are 0. ഇപ്പോൾ ചാർജ് സീറോ, ചാർജ് ഡെൻസിറ്റി സീറോ ആണെങ്കിൽ അത്തരം കേസിൽ വരുന്നതാണ് ലാപ്ലേസ് ഇക്വേഷൻ. The Poisson equation is del square phi is equal to minus rho by epsilon 0, where rho is volume charge density per unit volume. In a charge-free region, in a charge-free region, rho is 0. So you put rho is equal to 0 in the above equation. That is, del square phi is 0 by epsilon 0. That is, del square phi is 0. This is Laplace equation. So there is only a small difference between the Poisson equation and Laplace equation. Laplace equation is del square phi is 0. Poisson equation is del square phi is minus rho by epsilon 0. That is, Poisson equation reduces to Laplace equation in a charge-free region. That is all. And there is a problem relating the questions relating the Laplace equation. The first question, state Poisson Laplace equation. So you have to derive the Poisson equation also. And there is a problem. Show that the potential function v is equal to x square minus y square plus z satisfies the Laplace equation. Solution. V is x square minus y square plus z. Laplace equation is del square phi is 0 or del square v is 0. You put a v in its place. Del square v is equal to del square of x square minus y square plus z. You write the expression for del square. Del square v is dou square by dou x square plus dou square by dou y square plus dou square by dou z square of x square minus y square plus z. When we differentiate x square twice with respect to x, we get 2. Similarly, for y square minus y square, we get minus 2. And for z, the second derivative vanishes. So the result is 2 minus 2 plus 0. I think the differentiation is very clear. When we differentiate x square twice with respect to x, we get only the constant. First derivative is 2x, second derivative is 2 into 1, 2. So the result is 2 minus 2 plus 0. That is 2 and 2 cancel. We get 0. Del square v is 0. That is Laplace equation satisfied. But തന്നിരിക്കുന്ന പൊട്ടൻഷ്യലിൽ ഇവിടെ Laplace equation ശരിയാകും. We see a similar problem. Show that the potential function v is x square plus y square minus 2z square satisfies the Laplace equation. Solution is del square v is 2 plus 2 minus 4. When we differentiate 2z square, we get minus 4. So 2 plus 2 is equal to 4, 4 minus 4, 0. Here also, del square v is 0. The Laplace equation is satisfied. Another question, a similar question. Show that the function g equal to square plus y square does not satisfy the Laplace equation. ഇത് ലാപ്ലേസ് ഇക്വേഷൻ ശരിയാകില്ല. ലാപ്ലേസ് ഇക്വേഷനിൽ സാറ്റിസ്ഫൈഡ് ആകില്ല തെളിയിക്കുക. ഷോ ദാറ്റ് ദ ഫംഗ്ഷൻ g is equal to square plus y square does not satisfy the Laplace equation. Solution: del square g is del square of x square plus y square. As you have seen, 2 plus 2, 4. That is, del square g is not equal to 0. Therefore, Laplace equation is not satisfied here. And this is a short answer question, a university examination question. What is the importance of Poisson's equation? Poisson equation പ്രാധാന്യം എന്താണ്? Importance of Poisson equation. It's a second degree differential equation. It is useful to solve a potential V as a function of a position, which is the potential distribution. That is, these equations help to This equation means we can write any number of equations. These equations help to find V, E, D. D is electrical displacement, a new term that we see later. B potential, E electric field, D displacement, J current density, I current, etc. അപ്പോൾ എന്താണ് ഈ പോയിസൺ ഇക്വേഷൻ്റെ പ്രാധാന്യം? അതായത് പൊട്ടൻഷ്യൽ അത് സോൾവ് ചെയ്യാനായിട്ട് വി കണ്ടുപിടിക്കാനായിട്ട് നമുക്ക് സഹായിക്കുക ഇക്വേഷൻ. ഇറ്റ് ഈസ് യൂസ്ഡ് ടു സോൾവ് പൊട്ടൻഷ്യൽ വി ആസ് എ ഫംഗ്ഷൻ ഓഫ് പൊസിഷൻ വിച്ച് ഈസ് ദി പൊട്ടൻഷ്യൽ ഡിസ്ട്രിബ്യൂഷൻ. അത് കണ്ടുപിടിക്കുക. That is using these equations. In the Poisson equation, we can write a number of manner for number of potentials. So these equations help to find out V, E, D, J, I, etc. J current density and D is the electrical displacement. അപ്പോൾ ഈ വിലകളെല്ലാം നമുക്ക് കണ്ടുപിടിക്കാൻ ഈ പോയിസൺ ഇക്വേഷൻ സോൾവ് ചെയ്താൽ മതി. അതാണ് അതിൻ്റെ പ്രാധാന്യം. With this, our lecture on Poisson and Laplace equation, Poisson equation and Laplace equation is over. The next class we come with another topic. Thank you very much.